This is the second video about exploratory graphs. So remember from the first video that the reasons that we use graphs in data analysis are both for our own personal understanding as well as to communicate results to other people. And so exploratory graphs, as you'll recall, are mostly focused on creating graphs that are useful for you as the data analyst, and the goal is not necessarily to communicate them to other people. We'll talk about communicating with graphs in the next lecture. So remember that the characteristics of exploratory graphs are primarily that they're made quickly, you make a large number, and that you don't necessarily take time to clean those graphs up. So we're going to go back to the housing data that we've been using as an example. So this is, again, reading in the housing data as a CSV file. If the file is ss06pid.csv is in a different directory, you'll need to change the path before reading the data in. So the next type of plot that we're going to be looking at is what's called a scatter plot. So this is the type of plot that you're starting to make to be able to make visualize relationships between variables. We're going to be talking a lot about scatter plots because scatter plots are probably the most widely used graphical tool for exploratory data analysis. So the components or the parameters that are important for a scatter plot are x and y. Those are the two variables that you'll be plotting. Also the type, we'll talk about what that means in a minute. xlab and ylab are commands that are the parameters that let you set the variable names that appear for the axes here. xlim and ylim let you set the width and the length of the axes. cex is the sort of the size of the points that you see. Color is the color of the points, and bg is sort of the background of the points for specific kinds of points. So if you want to see a lot more about the different kind of parameters, and there are a ton that you can set for scatter plots, you can type !par, and that will tell you a lot about all the different kind of parameters that you might set. So first we're going to talk about a scatter plot, and in R, since it's sort of the most important plot for performing data analysis, it gets the plot command. So we just type plot, and then we give it two variables that are quantitative. In this case, we're going to plot commuting time, JWNP is commuting time, versus wage. So this is the actual wages that you earned in the last year. I'm going to tell it to use PCH equals 19. So this is actually the character type that it's going to use for the plot. If you leave it as default, it'll use open circles for the plot, but here I like closed circles better. And then I'm going to set the color to be equal to blue. And so what you see here is a scatter plot where you've got on the x-axis is the first variable that you pass to plot, and on the y-axis is the second variable, and each point represents one of the observations of that you've passed into these variables. So you get a point here means that for this data value in the vector of commuting times and wages, it had a commuting time in minutes of something like 70 minutes, and this person had a wage of something like $150,000. And so the plot actually has to be made with two variables that are of the same length. So the commuting time and the wages have to be of the same length if you're going to make a scatter plot, because each of these points corresponds to one of the points in the two vectors. So one of the things that you can see right away is you can see sort of strange patterns in the data set. Like, for example, here you got this straight line, which are a bunch of people with the same reported wage, but different actual values of the commuting time. And so you might think, this seems sort of strange. It might be because of the way that the data are coding, and indeed if you go look at the way the data are coded, you'll see that these values appear all in a line because of the way that the data are coded. So in addition to sort of visualizing the relationship between the two variables, if there is one, you can actually sort of pick out particular problems with the data or sort of weird patterns in the data that you don't think are necessarily due just to chance. They might be due to the way that the data were collected. So another thing that you can do on that previous plot, you could see that some of the points were sort of hard to see the difference between them. So you can change the CEX parameter, CEX equal to 0.5 here. And so now I actually see that the dots are a little bit smaller, and so you can see the separation between dots a little bit better. You could actually make it even smaller than that, and you would sort of break up some of this chunk down here in the lower left-hand corner, which is a little bit hard to see. So the size of the points matters. Also the size of the axes matters. If you set the xlim and ylim, it might be easier or harder to see these points. You can also use color, similar to the way that we used color in the box plots in the previous lecture. And so what you can do is, again, you're going to send two continuous variables to the plot command. So we're going to use, again, the commuting time and the wage. And again, I'm going to set the PCH equal to 19 because I like the filled in circles. But now I let the color of the points be equal to this variable sex. So if you look at this variable sex, it takes on values 1 or 2. To be able to do this trick that I'm doing right now, you have to pass the call parameter, the color parameter, a vector that has actually integer values. So in this case, it's 1 and 2. You shouldn't try to do this if your variable, say, is if sex was equal to either male or female, then it wouldn't necessarily work. And again, I set the CEX equal to 0.5, so it's either the C. And so now what does this plot show? It's, again, commuting time on the x-axis and wage on the y-axis. But you see that all the values where sex is equal to 1 are in black, so those are the males. And all the values that where sex is equal to 2, those are the females, are in red. So you can actually see that there's slightly different distributions for the men versus the women. In particular, you see that there's only one red dot up here and there are a number of black dots. And so it gives you some ideas about not only the relationship between these two variables, but how it's different based on a third variable. So it allows you to basically expand it beyond 2 dimensions when you're making this type of plot. And this is a very common thing to do. You'll see it in my example data analysis that I've used color frequently to illustrate a third variable when I'm showing the relationship between 2 other variables. You can also use size to illustrate the third variable. This can be really useful in some cases and kind of hard to see in the other cases. So here what I've done is I've actually calculated a variable. This is a new variable that is the percentage of the max age that each value is. So I take the ages of the individuals observed in the study and I've divided by the maximum age. So what I get is the percentage of the max age left. And so what I can do is actually make a plot again of these two variables, the commuting time versus the wage, and I can make it in blue with the filled in circles. But now what I can do is I can make the size of the points proportional. In this case, it's half of the percentage max of the age. And so what you can see is, again, you see all of the sort of the data points by wage and commuting time. And you can see that the points that are really, really small correspond to individuals that are actually sort of younger, and the points that are much larger correspond to individuals that are older. So like I said, sometimes this can be really useful to be able to use size, because you can also use size and color in combination to try to visualize the relationship between 4 variables. But in this case, it's a little bit hard to see. The difference between these dots, unless you have a very eagle eye, is pretty hard to tell. And so using size is useful, but it should be reserved probably for if you're already using color for something else. So the other thing that you can do is when you're creating these plots, you can start overlaying lines or plots, lines or points on these graphs so that you can sort of visualize relationships. So again, I make the plot of wages versus commuting time here, and then I can use the lines command just like I did before with the density plots. And what I can do is I can actually plot, in this case, what I'm doing is I'm just repeating the value 100 a bunch of times for the x values, and then I'm actually plotting the wages on the y values. And so what that does is, since the x value, there's only one x value and a bunch of y values, it makes a vertical line. And I can make that in gray with, and set the width of the line that I'm going to make. I can also add sort of points to a plot. In this case, I'm going to add points where the x values are a sequence from 0 to 200 in equal intervals, and then the y values are a sequence from 0 to 20,000 or 200,000 in equal intervals as well. And so what you can see here is that I have a set of dots that line out along those values. And so in this particular case, this set of dots and this line aren't necessarily useful, although this line might tell you, these are only the individuals that have, on the right-hand side, that have a commuting time greater than 100, and on the left-hand side, less than 100 minutes. But you can use these sort of lines and dots to give yourself breakpoints in the picture and to communicate specific results. We'll also use these commands, lines and points, to actually add the fitted values from models once we get to statistical modeling. The other thing that you can do is you might want to be able to visualize numeric variables as factors. So sometimes what you want to be able to do is make a plot here again of the relationship between commuting time and wage, and you might want to be able to break it down by age. And as I showed you previously, breaking it down by age was actually kind of hard to see if we used the size of the points to represent age as a continuous variable. So what you can do is you can break age up into a factor. And so remember, the cut2 command takes this continuous variable and breaks it up into 5 equal intervals and then assigns each point as a factor to one of those different intervals. And so what we can do then is when we make this plot, we can actually color the plot by the age groups that I've created. And so now the plot will have 5 different colors, one corresponding to each of the different age groups. And so this makes it easier to sort of see if there's a difference in distribution across the ages. It doesn't appear that for this plot there's a big difference in the age distribution comparing wages and commuting time. But in other plots it might be really useful to be able to see if there's a sort of relationship that's modified by a third variable, and one way that's very common to do that is with this factor. A really common occurrence is when you're making a scatter plot is that you'll have a large number of points. So in this case I've created 2 vectors x and y, and each of them has about 100,000 points, and I plot them against each other, again with filled in circles as the character that I'm using to make the plot. And you can see that it actually ends up just looking like a big lump of black. And the reason why is because all of these points overlay each other, and so you actually can't see the distinctions between those points. So this is a very common occurrence, and it's sort of not informative what's going on here in the middle. You might not know if there's a ton of points right here in the center, and there's also a large number here, but not quite as many. So it's a good idea to be able to try different things to see what's going on when you have a large number of points. One idea is to sample the values. So we talked about sampling in the earlier lectures. And so what I can do is, again, generate that x and y value. And what I can do is sample observations, say 1,000 observations between the x and y values. You want to actually sample the same values for both x and y because you actually want to plot the values of x versus the values of y that you've observed. And so what I can do is then subset x by the sampled values and subset y by the same sampled values. And I get a plot that looks a little bit less like a black ball here in the middle and looks a little bit more like a set of points. I could actually subsample even further if I wanted to be able to see the plots more neatly. Since I've taken a random sample, I still get an idea of the relationship between these 2 variables. Particularly for exploratory analysis, you don't necessarily need to see all of the points. A random subsample of the points can give you a big idea about the relationship between the variables. Another option is to use what's called a smooth scatter. So again, I have the x variable and the y variable, and if I, instead of saying plot, I use smooth scatter and x and y, what it does is it creates what's called a smooth density plot. So what this does is it shows places where there are lots of points in darker colors. So the dark here in the center means that there's a lot of points there. Then there get to be slightly fewer points in this ring here, and then slightly fewer points as you go farther away. And then it shows individual outlying points as hard dots like this. So what this allows you to do is to visualize the relationship between these 2 variables without actually having to see all of the points themselves. Another way that you can do this is with the hexbin package. And so what you can do is you can take x and y and create a hexbin object using x and y. And so what that does is it breaks the set of y values and the set of x values up into these hexagonal bins. And then what it does is it counts the number of points in each hexagonal bin. And so again, you see darker colors mean that there are more points. So there are more points here in the center than in the bins that are sort of farther and farther out here on the outside. So this is another way that you can sort of visualize when you have a lot of different points, a lot of points, you can visualize the relationship between x and y. So another type of plot is called a QQ plot, and this is sort of like a scatter plot, but has a very particular purpose. And so what it does is it takes 2 variables. Again, you're going to be usually looking at quantitative variables with QQ plots. So I've generated x and y are quantitative variables, and I pass it to this command qqplotxy. And what that does is it plots the quantiles of x versus the quantiles of y. So you can think of it as this is the sort of the smallest quantile or percentile of x versus the smallest percentile of y. Say this is the the first percentile all the way up to, say, the 100th percentile of x and y. So if the 2 distributions are exactly the same, you'd expect these quantiles to land perfectly on the 45-degree line, which I've shown here using the AB line command. So the AB line command takes two parameters. This is equal to the intercept, and this is equal to the slope. So if you give it the parameters 0 and 1, it actually just makes the 45-degree line. And so what we can see is that the quantiles down here for y are slightly larger than the quantiles for x. And so this gives you a little bit of information about the distributions. This will be particularly useful if you're looking at normal distributions and you want to see if your data are normally distributed. You can make a QQ plot with normal data versus the observed data, and you can see if there's large deviations from this line that the data are likely not normally distributed. I'll show plots like this as we go on in the modeling section of the course. The other thing that you can do, and this often comes up, is that you have data where you want to plot actually observations over time or observations that are observed longitudinally. So what we've got here is a matrix X. And so I'm generating, again, a random matrix. So it's a matrix that has 20 rows and 5 columns. And so I just generate 100 normal random variables and put them into that matrix. And then what I'm going to do is I'm going to use Matplot to actually be able to plot the different columns of that matrix. So what Matplot does is it takes each column and will plot it as one specific line. So the black line with the ones is the first column of observations. The red line with the twos is the second column of observations, and so forth. And so what this allows you to do is if you've observed data over the time, you can actually compare the trends or trajectories over time by looking at the trajectories across columns. So this is commonly used when you're doing either longitudinal or time series data analysis. And they're also called spaghetti plots because this plot kind of looks like spaghetti, I guess. Another kind of plot that you'll be seeing a lot of in this class are heat maps. And so what a heat map is it's sort of like a 2D histogram. So what I've done here is I made an image. I use the image command to make the heat map. And what it is so I have a matrix of values. So in this case, I took the values from our data set that are in the first 10 rows and in columns 161 to 236. And so I made an image of those where the brighter the color in this case, the larger the value. So the white here is the largest value and the red are the lowest values. And so what you can see is you can actually visualize the whole matrix of observations that you've got all in one plot. And color represents the sort of intensity or the size of the observation that you have. So this, if you have sort of a good eye, you'll see that this is a little bit, when you make an image plot using the image command, it's a little bit confusing because the first thing that it does is it sort of makes a transpose of the data. So remember, we're looking at columns 161 to 236 of the data set, but in the image, the columns are actually placed in the rows of this image. So to sort of make it match your intuition of what should be in rows and what should be in columns, you actually have to do this kind of funky transformation. And so what you do is you create your new matrix is just a matrix of the data set. So this was a data frame before, and I'm just changing it to have class matrix. This is only done because I need to use a matrix to be able to perform the operations that I'm going to perform here and pass to the image command. And so what I do is I take the transpose of the matrix and then I reorder it so that the sort of the columns of the transpose are flipped order. So this seems like a crazy command, and there's no intuition or rhyme or reason behind it other than the fact that when you do this particular flipping and reordering of the data set and then make the image, you now get in the rows rows of your data set, and in the columns of your data set, so that the image maps a little bit more to your intuition about what this matrix should look like. So you'll be seeing this transpose and then flipping the rows come up over and over again when I make a heat map. And again, remember, the only reason why I'm doing that is so that the image matches your intuition of the matrix. So I'm going to give you, this is another area where there's a huge amount of information that you could learn about plotting on geographic maps, but I'm just going to show you the very basics in R. So if you use this maps package, if you load the maps library, and you type map of the world, you'll get actually this map here with all the black lines representing the actual geographic outline of the world and the countries in the world. You can then generate some latitude and longitude values. In this case, I've just generated them randomly. And if you add points to this map, you can actually add points in latitude and longitude values, and they'll appear on the map according to the latitudes and longitudes that you've developed or that you've generated. So you can also use different maps. There's a map of the United States, there's maps of Europe, and so forth. If you look in the maps package, you can find a lot more about creating different kinds of maps and then overlaying points on those maps that represent your data. A quick note on missing values. So one of the things that you can use plots for is understanding patterns in your data, and one of the patterns that you'll very commonly run into is missing values. And so here I've generated a vector x that has 3 missing values at the beginning, and I've generated a vector y that has values 1 to 10. And so if I plot x versus y, I can see that the first 3 values just don't appear on the plot. So what R does is anytime it sees a missing value in a scatter plot, it's just not going to plot that point. That's an important thing to keep in mind, because if you have missing values and they're contributing to changing what the patterns between the 2 variables are, the relationship between the 2 variables, if you don't deal with the fact that R just sort of skips those over, you might get sort of inappropriate or incorrect conclusions from the graph that you're making. Another thing that you can do, though, is use the box plot command that we saw earlier and actually see the distribution of NAs comparing different groups. So here I've generated 2 vectors x and y, each of 100 normal random variables. And then I create all of the values where x is less than 0, I make to be NA values in the y vector. And so then what I can do is I can actually say, okay, is there a relationship between the missing values in y and the values of x? And the way that I do that is I make a box plot of x, and again I use this tilde to say, okay, I'm going to compare values where y is equal to NA or y is not equal to NA. And so if you do that, you can actually see very clearly that when y is equal to NA, the x values are small, and when y is not equal to NA, you see the x values are big. So this type of plot can actually be used to explore the data and see if there's relationships between missing values and the other variables in your data set, which might lead to incorrect statistical conclusions from your data. So I have just barely scraped the surface of graphing in R, even for exploratory graphics. And so I'm going to give you some resources here. The R graph gallery has a bunch of different graphs along with corresponding R code for making those graphs. ggplot2 and the documentation for ggplot2 are here. ggplot2 is an entirely different graphing mechanism apart from the base R graphing mechanism that allows you to make very pretty plots, but also allows flexibility in a lot of different ways for exploring data. Similarly, the lattice package is another add-on package that allows you to do a lot more flexible sort of plotting than you can in the base R package. Finally, I've linked here to a blog, R Bloggers, where people frequently post interesting R code for performing different kinds of graphs that might be useful for more sort of exotic data sets than we've been talking about here.